So, last time we finished up the class by just scraping the beginning of the intro to finite element analysis. And so, just a quick recap, right? We went through, these are the different types of two-dimensional problems that we're going to cover in this class. We defined the first three terms here. And so remember, at the beginning of the semester, we were talking about structural idealization, and we talked about how we idealize structures. We use points, lines, and areas. This is one of the places where that comes into play, right? So nodes are point elements. Element, we really kind of use the term element generally, but also specifically to refer more to line or area members. And sometimes member and element are terms that are used interchangeably too. In this class, with regard to finite element analysis, we're only going to be thinking about line elements, not area elements. But it is important to know that those do exist, and we do use them a lot in structural analysis. Degree of freedom, right? We define that as ways that a node can move that is tied to deformation of the structure. So we went back then and identified how many degrees of freedom each of these different types of systems represents, right? So for axial force systems, single axis axial force systems, right? Here we have, you can have movement along the axis, right? Well, I'll just, instead of drawing it, so we'll just add a note here that 1 degree of freedom is axial, right? And so that direction is specific to the orientation of the element. And we'll come back to that in a moment when we define global versus local systems down below. When you have multiple axes in an axial force system, again, that's really just a truss because it's an assembly of single axis axial force elements, right? But because we have multiple different orientations or angles of those elements, we need a way to represent the entire structure. So that's why we have 2 degrees of freedom, and that's going to be translation in X and translation in Y. For beams, right, we have 2 degrees of freedom. That's going to be not axial, pardon me. The 2 degrees of freedom, right, those are the ways that the beam nodes can move that are relevant to the deformation of the beam. And so that's going to be transverse deflection and rotation. All right, so whether it's single element or multiple element, those are the degrees of freedom that you are concerned with for beams. For frames, you're going to have axial, transverse, and rotation as your degrees of freedom, right? So with a frame, you can have all 3 possible degrees of freedom for a 2-dimensional analysis. In global terms, right, we'll come back to that as well. Right, it'll be X, Y, theta. And so it depends on the element, right? Whether axial could be X and transverse could be Y, right? That would be true if the element that you're looking at is horizontally oriented, or it could be the reverse, right? Transverse could be the global X and axial could be the global Y if you have a column. And then if you have an element that's at a diagonal, then your axial will have X and Y components, and your transverse will also have X and Y components. So that's something that we'll think about later. We'll actually introduce that concept in the context of trusses when we have to do coordinate transformation, because similar, right, with trusses, each individual member is going to have axial deformation. That axial deformation is going to be represented in terms of global X and global Y components for every member. So we'll talk about that later, maybe not this week, but maybe next week. we'll see how far we get today. All right, so continuing on with these definitions, boundary condition, right, or BC for short. A boundary condition is specifically your known displacement or force going into the problem. And these known displacements or forces are specifically at nodes. Stiffness method, in that term, refers to the finite element method or finite element analysis. It's just another expression for it. And it's often called the stiffness method because we use a matrix of stiffness coefficients to solve for these unknown values. So the general equation in matrix form is F equals K times X. Now you're familiar with that equation already, right? It's the equation for a linear spring. This may be the first time you've seen it in matrix form, and maybe also the first time you've seen it apply to not just one dimension or one direction of deformation or displacement, right? So we will ultimately be expanding this to accommodate all 3 degrees of freedom for frames. And the really cool thing about this method, by the way, is that not only are you able to use this to analyze and solve for your unknown displacements and deformations, or unknown forces, right? But you're also able to use it to obtain the deformations, right, and displacements. So that's one characteristic that is really powerful with this method. And then also we can use this method to analyze determinate and indeterminate systems. And continuing on with that, in fact, if you have an indeterminate system, or I should say the more indeterminate the system is, actually the easier the solution becomes. Because the more indeterminate a system is, the fewer unknown displacements you have, right? Think about that. Fewer unknown displacements you have, the more indeterminate the system is, right? We'll see that as we go through examples. And so what that ultimately means for you as we go through this method and your hand calculations, you'll have a smaller matrix to work with for your first solution, the first partition, right? When we solve for unknown displacements. So we'll get into that later. All right, so back to the stiffness method. Specifically, right, it relates external forces to displacements and again, this is specifically at nodes. And I really want to emphasize external in this, all right? So with this method, we are never concerned with internal forces through our solution. Once we have solved for all the external forces using finite element method, then we can go back and use that information to solve for any internal force that we're interested in at any point along the length of that structure, right? But for the duration of the finite element solution from beginning to end, we are only concerned with external forces at nodes, all right? So that's one thing that I'll probably be reminding you of over and over again throughout this because it's important. And it's easy, it's tempting to try to think about the internal forces and what's going on when you're solving these problems. But But it also makes it impossible to complete the method if you mix those up. All right, so external forces in this equation, right, F equals kx, the external forces are represented by the F matrix, right? So sometimes we use capital F, sometimes we use lowercase f. Sometimes it's a preference of whoever's writing it. So, and those forces could be reaction forces or applied forces. And also it is understood that when we refer to forces, displacements, we are including moments and rotations in those terms, right? So it's just worth noting. So now with regard to displacements, we use a few different symbols to represent displacements. Sometimes it depends on the context. Some of them are interchangeable. So you may see lowercase delta used to represent displacements. A lot of times this is reserved for representing axial deformation, but not necessarily. So you could break it down into x and y. Sometimes just x is used to generically represent any deformation or displacement. Sometimes we see capital delta, and then sometimes u is used. So you may see that. I think your textbook uses u in some contexts. And similar to how the forces includes moments, displacements includes rotations. All right, I'm going to highlight our equation. And then we'll come over here and provide a little sidebar on the global versus local comment. I already alluded to this earlier, but I'll just make a few notes here. So the reason we distinguish between global and local coordinates and displacements and deformations and forces is because depending on what we're after, in the overall solution, we're really focused on the entire system. And so when we're thinking in the context of the entire system, we need to have some global definitions to work with, right? So global is for system context. And then locally, all right, we're interested in what's happening to the individual element axially as far with regard to transverse deformations and rotations. So this would be like the element context. And as you'll see when we apply this to trusses, right, we'll first solve the truss using global results, and then we will be able to take those global results, plug them into a formula to obtain local results for individual elements. So our global system is usually the traditional Cartesian XY, where we often use capital letters X and Y to distinguish it from local notations. And then the local axis would be whatever aligns with the orientation of the element. So usually that would be the x-axis aligns with the axial direction of the element, and then the y-axis would be the transverse for the local element. All right, questions so far? All right, so now we're going to go through the rules. There are 7 of them. So first rule, and these apply to all types of problems that we'll address in this class. The number and type of degrees of freedom will depend on the type of system. We already talked about that up here, right, where we outlined how many degrees of freedom there are for each of these systems, right? So that's just restating what we already talked about. Second rule, each degree of freedom has 2 associated values, one tied to force and one tied to displacement. All right, so again, that could be an axial force and an axial displacement. It could be a force in the x direction and a displacement in the x direction, or it could be a moment and a rotation, and so on. Third rule, at each node, exactly one value per degree of freedom is known. All right, so that means exactly one of these 2 values that we defined above. We'll expand on that later. And this also ties to the next rule, which says that the force and displacement matrices will each have known and unknown values. All right, so going back to rule 2, what this means, all right, we just said each degree of freedom has 2 associated values. At each node, one of those values per DOF is known. So at some degrees of freedom, you might know the force, and at others, you might know the displacement, right? If you know the force, you don't know the displacement, and vice versa. So we're going to end up with force and displacement vectors that will have both known and unknown values in them. And that's where matrix partitioning will come into play. All right, so then the next rule, the stiffness matrix, which is K, this comes from the material and geometry of each element. All right, and the material property that's relevant is going to be, of course, Young's modulus. The geometric properties that are relevant depend on the behavior that we're considering. So we'll look at that when we start looking at individual systems. Sixth rule, we always solve for unknown displacements first. This one is really, really important. This one is so important. I'm going to be reiterating this over and over again. You'll probably get sick of me saying it, in fact. But it's really important because, as you will see with these problems, it will often be tempting, especially when you have a determinate system. It will be tempting to use statics to solve for the reaction forces and treat those as known values. But that is not the correct approach, and it will mess up your whole analysis for the structure using finite element method. So even if you can figure out the reaction forces in your head, and you will see problems like that, do not use them as known forces. Treat them as unknowns for this method, and then at the end, check those values, right, using statics against your results from the finite element method. So I'm going to be reiterating that a lot. And so that leads to the 7th rule. Do not use statics to find the reactions. All right, so next we'll talk about boundary conditions and how to identify them. So this ties directly to rules 3 and 4. All right, so I already sort of mentioned this. Where there's a reaction, all right, the force is unknown, right? Even if you can figure it out in your head, treat it as unknown, and the displacement is going to be the known value. So in this case, the displacement is your boundary condition because it is a known value. Where there's no reaction, the external force is your boundary condition because that is what is known. And in this case, then, the displacement is unknown. Now, there is an exception to this rule, and that is if you have a problem where there is an imposed displacement. That is beyond the scope of this class, though, so we won't have to worry about that, but it's worth noting. And then I'll just say, not applicable to this class. All right, so what this means is that at each node, for each degree of freedom, the external force is either a reaction or an applied load. And if there is no reaction, and if there is no applied load, the external force is still known, it's just 0, right? So that still counts as a known value, and it is your boundary condition for that degree of freedom. Second point here, the displacement will either be 0 or unknown. And again, that's in this class, right? The exception is if you have an imposed displacement, in which case it would be a known non-zero value. But in this class, we're only going to have known displacements that equal 0. How do we know if a displacement is 0? Exactly, yeah. If there is a reaction that is preventing motion in a certain direction, right? So it would be 0 due to a support. Or if it's unknown, then it could technically still be 0, right? It depends on what else is going on. But there's no support requiring it to be 0, so we treat it as an unknown. All right, so then a few comments on sign convention, and then we'll roll into applying this to axial force systems with single axis. So for the finite element analysis method, we always take positive to the right, positive up, and positive counterclockwise. So these are technically global directions, right? When we get into trusses that have different orientations, it'll be a little bit more specific, right? So we'll always have to think about positive in the axial direction from the lower numbered node to the higher numbered node and things like that. But generally speaking, right, here's your global sign convention. And I'll just note here, the exception is if we have truss or frame elements locally where the axial and transverse directions will vary. There it is. All right. All right, so let's get rolling with single axis axial force systems. So a lot of the notes are already written down here, so we'll have a little bit of writing to do, but essentially, right, we're going to just start off by identifying the specifics to this type of system. So as we noted earlier, right, axial stiffness in general is a function of material and geometry. But in terms of axial stiffness, the geometric properties that are relevant are the cross-sectional area and the length of the element. All right, the material property that's relevant is always going to be Young's modulus. So the axial stiffness will relate axial forces to axial deflections, and you are familiar with this in terms of capital delta or lowercase delta, right? From mechanics of materials, you learned this expression, PL over AE. So there you have your L and A for the geometric properties, and then E for the material property. And P, of course, is the applied force, or actually it's the internal force at the location where you're calculating displacement, right? When we apply this to finite element analyses, it's going to be applied forces. And you're also familiar with the equation for a spring, right? Here's the sign convention noted for single axis axial force systems. So in general, I'll make a note here. The positive direction will be along the axis from node I to node J. where I specifically is the lower numbered node. But whenever we have elements that are like this, just on a single axis or a beam element, we're always going to number our nodes left to right. So it'll be kind of easy and systematic to keep track of. All right, so at two ends of a spring, right, we have nodes 1 and 2 defined here. You've got the end or nodal forces, F1 and F2, and the end or nodal displacements, X1 and X2, defined and shown on the sketch. So we're going to assume that each node can only move in one direction. And that direction would be along the axis. All right, so it can move back and forth along the axis, but really only one direction of motion. So that would be a single degree of freedom. And we can relate the nodal forces to the nodal displacements, right, using these equations. If we assemble those equations in matrix form, it looks like this. Where we have a stiffness matrix that's a 2 by 2, consisting of positive and negative values of K. And then the displacements at each node on the right. All right, so if you look at this 2 by 2 stiffness matrix, you may notice that the determinant is equal to 0, right? So remember, with the 2 by 2, the determinant is the product of the main diagonal minus the product of the off diagonal. And so in this case, it's 0. Why is that a problem? Sorry, what's that?
We have to divide by that to get the inverse.
Well, yeah, right. So we can't get the inverse, right? Because we can't divide by 0. So the inverse does not exist. This represents a system with rigid body displacement. And as you know, because we've talked about this before, rigid body movement means what? Very good. Yeah, it's an unstable system. So we can't compute the forces and displacements under these conditions. In order to rectify that and turn it into a stable system that we can analyze, we need to impose boundary conditions, right? So the boundary conditions will stabilize the system. It will also allow us to analyze the problem. So that's on the next page. We will apply boundary conditions. Before we do that, though, we're going to add another spring to the system. All right, so we're going to make it a little bit more complex. And now we're going to do this to demonstrate how to overlay matrices with multiple elements. So now we have our relationship for the first spring, right? So this is the same as before. But now we also have a spring in between nodes 2 and a new node 3. All right, so that relationship is very similar, except we're just using a different stiffness value associated with that spring. And then I also have subscripts outside of the force vectors, noting that these are the values that of the forces associated with the behavior of the first spring, and these are the values or the portions of the force associated with the second spring. So what that ultimately means is when we combine these systems to overlay, we overlay the matrices to combine these systems and evaluate the entire system working together, right? We're going to be summing the forces at node 2, which is where the two systems connect, right? So we have the F22 plus F21 down here. So I'll just write out the equations for node 2 specifically, since that's where the overlap occurs. So we would have F21, just writing out this matrix, this row of the matrix equation, right, is equal to negative K1x1 plus K1x2. And then in the second spring, we have F22 is equal to K2x2 minus K2x3. So then in the overlay, we have F22 plus F21 is equal to negative K1 times x1, all right, that's that, plus K1x2 plus K2x2, and then minus K2x3. So if you think about these matrices independently first, all right, the stiffness matrix from the first spring and then the stiffness matrix from the second spring, the overlay, all right, will occur where those matrices overlap at the second node. So I guess I'll just note here to, right, we got that K1 and or wait, I reversed the colors. Here we go. K1, oh, I reversed them down below too. All right, I'll fix that. All right, so where they overlay will be the common node. We have a similar application. Oh, yes, question.
How would you determine the sign of like the K?
So this just comes back to the general force stiffness relationship between the two springs, right? So the force at node 1 will be equal to the stiffness of the spring times the displacement of node 1 minus the displacement of node 2, right? And similarly, the force at node 2, right, will be equal to the stiffness of the spring times how much node 2 displaces minus how much node 1 displaces. Yeah, so it comes from these equations right here. Yeah, any other questions? Okay. And so in the context of a bar element, right, we have a very similar setup, except now we're replacing just K with AE over L. So now this expression right here, this term, right, this is now our K, and delta is substituted for X, or you can continue to use X if you want. So you have your general F equals k times x, represented here. So this is the general axial force stiffness equation for a single element. Right, and once again, here we have a K matrix with a determinant of 0, so we run into that same problem. We need to apply boundary conditions to solve it. So we'll look at an example. We'll go through this with linear springs, which gets a little bit complicated, or not complicated, but just a lot to write in terms of the Ks, because we have K1 and K2. So it cleans up a bit when we look at the axial system. All right, so here we impose a boundary condition at node 1, right? So node 1 is restricted from motion. That stabilizes the system. We now no longer have rigid body displacement, so we can analyze this system. We also need an applied load, right, in order for this to be meaningful. So we apply a load at node 3, and remember our positive direction is to the right. So we want to start by identifying what we know at each node. Since this is a single degree of freedom system, we're going to know exactly one value per node, right? Because it's one value per degree of freedom is what we know. So at node 1, we know that x1 is equal to 0. All right, so that means we do not know F1. That's a reaction force. Even though we know it, right? We know what that is. We all know it. We're treating it as an unknown. We're pretending we have no idea what it is. At node 2, we know the applied force. There isn't one, so it's 0. That means we do not know the displacement. And at node 3, we know the applied force. It's positive P. That means we do not know the displacement. So sometimes it may be easier to think about, do you know the displacement at the node and then figure out the rest from there? For example, if node 2, right, you can look at that and you can say, well, I don't know the force, but I also don't know the displacement. There's no support there forcing it to be 0, right? It's going to move. You know it's going to move. You just don't know how much. So you can then identify x2 as an unknown, which means, oh, you must actually know the force. Since there isn't one, now I remember that means it's equal to 0, right? Because a lot of times if there's no force applied, that's a common mistake, is to think that you don't know what the force is. All right, so now assemble this in the matrix form. So I'm taking this equation right here, right? Because we set up that overlay already for 2 linear springs in series. So we got F1, F2, and F3. And we don't know F1. We do know F2, it's equal to 0, and we know F3 is equal to P. All right, so I'm just going to add in the known values there. That's equal to K1, negative K1, 0 in the first column, negative K1, K1 plus K2, and negative K2 in the second column. And then third column is 0, negative K2, and K2. That matrix is multiplied by the displacements, so x1, x2, and x3, where we know x1 is equal to 0, and we don't know the others. I like to always label the columns in the stiffness matrix just as a reminder of what they get multiplied by. All right, and because x1 is equal to 0, that's our boundary condition, right? That means that all the values in this column are going to be multiplied by 0. So we can effectively just eliminate that column from our matrix for the analysis moving forward. So then the first partition of our equation, right? Remember that rule. We always solve, I think it was rule 6, right? We always solve for the unknown displacements first. So our unknown displacements are x2 and x3. All right, so that's going to be columns associated with x2 and x3. And we're going to take the rows that are associated with those degrees of freedom, right? Because those are the rows that have known forces. So we're going to take rows 2 and 3 and write what we have. 0 and p are equal to k1 plus k2, negative k2 in the first column. And then in the second column, we have negative k2 and positive k2. That's going to get multiplied by x2 and x3. x2 and x3 are what we're trying to solve for. So we need to invert this K matrix, pre-multiply both sides to solve for those displacements. All right, so we'll just quickly write the inverse here. That's going to be 1 over K1 times K2 times K2, K2 in the first column, and then second column is K2, K1 plus K2. So that's going to go into your equation, right? So we're going to pre-multiply that by 0 and p to solve for those unknown displacements at nodes 2 and 3. And the result will be p divided by k1 for x2, and then k1 plus k2 divided by k1 times k2 times p for x3. So you'll notice the results, right, for the displacements are all in terms of the applied force to the system and the stiffnesses of the two springs. All right, so then the last part would be, I know we're out of time, but the last part would be to go back to that first equation right here, right? F1 is equal to negative K1 times x2 plus 0 times x3, and find that reaction force. And you would get negative p for F1. All right, so that checks out with your gut, your intuition. We all knew that just by looking at the system. It also checks out with equilibrium. All right, any questions? So moving forward, right, the good news is I'm not going to give you any problems that are linear springs, so you don't have to deal with the K1, K2 nonsense. We're going to be looking at axial bars, so everything will be in terms of A, E, and L. All right, so next time we'll start off by looking at an example that's exactly like the one we just did, but with axial bars. Just talk about it a little bit, and then we'll move on to trusses. All right, well, we'll look at a few other examples first, and then we'll move on to trusses. Okay. All right, well, thank you all for your attention, and I will see you on Friday.